Let me tell you something, and I want you to listen carefully, because everybody's looking at this thing the wrong way. 4 people are in space right now as I'm talking to you. They're inside a capsule called Orion, somewhere between the moon and the Earth falling home. They launched a week ago. They flew around the moon 2 days ago. And on Friday, 2 days from now, they have to come back through the atmosphere at 25,000 miles an hour and not die. And everybody's celebrating. Everybody's talking about how beautiful the pictures are, how historic the mission is, how we're going back to the moon, and look, the pictures are beautiful. It is historic. But I want to ask you a question that nobody on TV is asking, and it's the only question that actually matters. Do we know this works? Not do we believe it works. Not are we hopeful it works. Not did a committee of very smart people sit in a room and agree that it works. Do we know because there's a difference? And that difference, the gap between knowing and believing, is where people die. I've seen it happen. I'll tell you about that. But first, let me tell you what this mission actually is, because I think you've been given the wrong impression. Artemis II is not a moon landing. I know. The news makes it sound like we're back, like it's 1969 again, like somebody's about to step off a ladder and say something poetic. That's not what's happening. Nobody's touching the moon. Nobody's walking on anything. The spacecraft flies to the moon, goes around the backside and comes home. A flyby, 10 days, start to finish. And if that disappoints you, if you hear flyby and think, well, what's the point, then you don't understand what's actually going on. See? Going to the moon is not the hard part. I know that sounds crazy, but think about it. Going to the moon is pointing a rocket in the right direction and burning fuel. We figured out the math for that 60 years ago. Newton figured out most of the math 300 years ago. The moon hasn't moved, the equations haven't changed. Getting there is a solved problem. The hard part, the part that should worry you, is everything else. It's keeping 4 human beings alive inside a metal box for 10 days, 250,000 miles from the nearest anything. It's trusting that every valve, every seal, every line of code, every weld, every bolt will do exactly what it's supposed to do in a place that is trying in every possible way to kill the people inside. Artemis II is a test. It's NASA asking, can this spacecraft keep humans alive in deep space? And I'll tell you something, if you're going to test something, a flyby is exactly how you do it. You don't test a bridge by driving a school bus over it on the first day. You test the bridge. Then you drive the bus. Artemis II is testing the bridge. The question is whether the test is honest, whether NASA is really looking at what it finds, or whether it's already decided what the answer is going to be. I have some experience with that. Let me tell you what it's like out there, because I don't think most people appreciate this. You live in a cocoon. You don't notice it. You've never noticed it because you've never been outside of it. You have an atmosphere, 100 kilometers of gas held down by gravity, pressing on you at 14.7 pounds per square inch. That atmosphere gives you air to breathe, sure, but it also blocks radiation. The universe is throwing particles at you all the time. Cosmic rays, solar wind, ultraviolet, and you never feel any of it because the atmosphere absorbs it before it reaches you. It's like living inside a shield you can't see. You have a magnetic field. Earth's core is a ball of spinning molten iron, and it generates a magnetic bubble thousands of miles wide. That bubble deflects the solar wind, charged particles screaming out of the sun at 1,000,000 miles an hour. Without it, those particles would strip away the atmosphere and sterilize the surface. You want to know what a planet looks like without a magnetic field? Look at Mars. That's what happens. You have temperature stability. Right now, wherever you are, it's probably between -40 and +50 Celsius. Perfectly manageable in space. In direct sunlight, surfaces hit 120 Celsius. In shadow, -150. Sometimes both of those temperatures exist on the same object, inches apart at the same moment. Metals crack from that. Seals fail from that. You have gravity, keeps your blood where it should be, keeps your bones dense, keeps your muscles from melting. Take gravity away and the body starts to come apart in slow motion. Fluid shifts to the head. Bones thin out. The heart reshapes itself because it doesn't have to work as hard. And you have rescue. Something goes wrong where you are right now. Help arrives in minutes. Worst case, an hour. There are systems stacked on systems designed to catch you. Now take all of that away, every single layer. No atmosphere, no magnetic field, no stable temperature, no gravity, no rescue. That's where 4 people are, right now. That's where Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen are sitting inside a cabin the size of 2 minivans, 330 cubic feet of habitable volume, hurtling through the void on flight day 8 of a 10-day mission. And look, this is the part that gets me. Within hours of launch, the toilet broke. The toilet. They got an amber warning light on the waste management system. Suspected ice blockage. For a stretch of the mission, the crew couldn't urinate in the toilet and had to use bags. The most advanced crewed spacecraft ever built, headed for the moon, and day 1, the plumbing fails. Now they fixed it. Ground controllers worked the problem. The crew troubleshot. It came back online. Fine. But that little episode tells you something important about what happens when you put human beings inside a machine. Humans are messy. Humans breathe and sweat and produce waste and generate heat and have emotions. An uncrewed capsule doesn't have any of those problems. The moment you add people, everything changes. And in deep space where there's no lifeboat, no quick trip home, no one coming to help, everything changing is a very serious thing. 2 days ago, April 6th, something happened that I want you to understand. Really understand, not just the facts of it, but what it means. At 6:44 in the evening Eastern Time, Mission Control in Houston lost contact with the Artemis II crew. Now, this was planned. This was expected. As Orion swung around the far side of the moon itself blocked all signals between the spacecraft and Earth. Radio, laser, everything blocked. For about 40 minutes, there was no communication at all. Zero. Think about what that means for those 4 people. They were 252,760 miles from Earth, farther than any human being has ever been, breaking the record Apollo 13 set in 1970 by more than 4,000 miles. And during those 40 minutes behind the moon, there was nobody to call, no ground controller to consult, no abort to trigger. If something went wrong, an alarm, a malfunction, a leak, they were on their own, 4 people and a machine and whatever they knew how to do. And what were they doing? They were looking at the moon. They came within 4,067 miles of the surface, close enough that it filled their windows like a basketball held at arm's length. They saw the far side with their own eyes, not through a camera, not on a screen, with their eyes. They may have been the first humans ever to see certain parts of the far side without a lens in between. "We love you from the moon," Victor Glover said before they disappeared behind the far side. You know, Mike Collins, the Apollo 11 astronaut who stayed in the command module while Armstrong and Aldrin walked on the surface, he orbited alone behind the moon. 48 minutes of silence. He said later he felt truly alone and isolated from any known life. But he also said he wasn't scared. He said he felt peace, that silence, that absolute aloneness. 57 years later, 4 new people felt it, and now they're on their way home. And the hardest part, the part that should scare you, the part that scares me, hasn't happened yet. Let me tell you about it. The heat shield. This is the thing. This is the crack. This is where my question, do we know this works, stops being abstract and becomes life or death. Here's the situation. When Orion comes back from the moon, it hits the atmosphere at about 25,000 miles per hour, Mach 32. At that speed, the air doesn't just warm up, it becomes plasma. The temperature on the heat shield reaches nearly 5,000 degrees Fahrenheit. That's close to the surface temperature of the sun. The heat shield is made of a material called avcoat. It's ablative. It works by charring and flaking away. Each layer that burns off carries heat with it, protecting the layers underneath. The idea is simple. The execution is extraordinarily hard. On Artemis I, The uncrewed test flight in 2022, the heat shield worked. The capsule survived re-entry. Splashed down in the Pacific. Mission declared a success. But when they pulled the capsule out of the water and looked at it, really looked at it, they found something that was not in the plan. Gouges, deep ones, holes in the avcoat blocks, not the smooth, gradual charring the models predicted. Chunks had blown out during re-entry. Pieces of heat shield material ejected into the hypersonic airstream, and the separation bolts, big bolts, embedded in the heat shield, packed with heat-resistant material, 3 out of 4 had melted through. Now this is where it gets uncomfortable. And this is where I need you to pay very close attention. NASA's first instinct was to minimize it. The early press releases said the rocket and spacecraft had performed exceptionally. It took months before anyone officially mentioned the heat shield damage. When they did, the program manager said they had observed more variations than expected, and the material had ablated away differently than what our computer models predicted, differently than predicted. That's a hell of a phrase. It wasn't until May 2024, a year and a half later, when the Office of the Inspector General released photographs, that the public saw what had actually happened, and the OIG didn't just show pictures. They identified 3 separate ways the damage could kill a crew: burn through from the gouges, debris striking the parachute compartment, hot gas ingestion through the melted bolts causing structural breakup, 3 paths to dead astronauts, on a heat shield that had been called successful. So NASA investigated, convened a panel, and in December 2024 they announced a root cause. The avcoat wasn't permeable enough. Gas got trapped inside the material during re-entry, pressure built up, and pieces blew out. The skip re-entry trajectory, where the capsule dips into the atmosphere, skips back up, then comes in again, made it worse by creating 2 separate heating phases. And then they said for Artemis II, we'll change the trajectory, steeper, more direct, less time in the heating regime that caused the problem fixed. But here's what should make the hair on the back of your neck stand up. The heat shield on Artemis II was manufactured with tighter, denser material than the one on Artemis I, designed that way to make ultrasonic testing easier. Several independent analysts have pointed out that this could make the shield more susceptible to the exact gas trapping problem that caused the Artemis I failure. NASA disagrees. They say the trajectory change more than compensates. But the models they used to reach that conclusion are the same models that didn't predict the problem in the first place. You see the circularity, you see the problem. I saw this before. I saw it with the shuttle. And the story of what happened there is the reason I'm talking to you right now. January 27th, 1986. The night before Challenger launched, it was cold in Florida, unseasonably cold. Ice was forming on the launch pad. You could see it on the metal structures hanging in sheets off the gantry. The temperature was dropping toward 28 degrees, colder than any previous shuttle launch. That night, a group of engineers at Morton Thiokol, the company that built the solid rocket boosters, got on a phone call with NASA managers. And those engineers said, don't launch tomorrow. The O-rings that seal the joints between booster segments get stiff in the cold. We have data showing erosion and charring on O-rings from previous flights. We don't know how they'll behave at this temperature. We've never launched this cold. Don't fly. And you have to picture this phone call. It's late at night. The engineers have their data spread out on the table. Charts, photographs of damaged O-rings from recovered boosters. They're pointing at evidence of charring from previous flights. Not catastrophic, not enough to have caused failure, but there, visible, measurable. Getting worse. And here's what NASA managers said. They didn't say thank you for the warning, we'll scrub the launch. They said prove it's unsafe. Think about that. They reversed the burden of proof. Instead of requiring the engineers to prove the system was safe, which is how it's supposed to work, they demanded the engineers prove it was dangerous. And when those engineers, sitting in a conference room in Utah, couldn't definitively prove a negative with enough mathematical certainty to satisfy managers in Florida who didn't want to hear it, NASA launched. The next morning, 73 seconds after liftoff, A plume of hot gas burned through the right booster's O-ring joint. It hit the external tank. The tank ruptured. The shuttle broke apart at 46,000 feet. Krista McAuliffe, Gregory Jarvis, Judith Resnick, Ronald McNair, Ellison Onizuka, Dick Scobie, Michael Smith, 7 people dead. Because the institution couldn't tell the difference between we believe it's safe and we know it's safe. When I investigated this, when I sat on the Rogers Commission and pulled the threads apart, what I found wasn't one bad decision. It was a drift, a slow, quiet, invisible drift that had been going on for years. The O-rings showed damage on early flights. Engineers flagged it. Management looked at the data and said, we flew and nothing failed, within acceptable limits. The next flight, more damage, within acceptable limits, still fine. Next flight, more, still within limits. Each time, the boundary of acceptable moved a little further from the original design specification, not because anyone decided to lower the standard, because the organization, under schedule pressure, under budget pressure, under the weight of promises made to Congress, did what organizations do. It got comfortable with risk it shouldn't have been comfortable with. There's a name for this: normalization of deviance. Abnormal becomes normal not because the physics changed, but because the people changed. They stopped seeing the warning signs as warnings. They started seeing them as features. 17 years later, Columbia, same pattern. Foam shedding from the external tank had been seen on flight after flight, each time photographed, documented, noted, each time declared acceptable, until a piece of foam the size of a briefcase broke off during launch, punched a hole in the leading edge of the left wing, and when Columbia came home, February 1st, 2003, over East Texas, the superheated plasma of reentry poured through that hole and the orbiter came apart. And 7 more people died in the clear morning sky. Same institution, same drift, same gap between knowing and believing. Now, I'm not saying the Artemis II heat shield is the next O-ring. I'm not saying those 4 astronauts are going to die on Friday. It is very likely, hopefully, very likely that they'll splash down safely off San Diego and everything will be fine. But I am saying this, the pattern is visible. Unexpected damage on Artemis. Eye damage declared acceptable. Root cause attributed to a mechanism the models didn't predict. Fix applied using the same models that missed the problem. Decision to fly based on analysis that cannot be independently verified because the test facilities can't replicate actual reentry conditions. And a former shuttle astronaut, Charles Camarda, who used to be the director of engineering at Johnson Space Center, looked at all of this and said, this is Challenger again. This is Columbia again. Not the same failure, the same reasoning, the same institutional behavior. The same gap between what the engineers know and what the managers believe. He published a detailed analysis. He was invited to a NASA briefing. He came away more alarmed, not less, and NASA flew anyway. On April 1st, 4 people climbed into that capsule and rode that heat shield into the sky. The question I'm asking you, the question I've been asking since 1986, is simple. What do we actually know, and what are we just telling ourselves? That question isn't history. It's not 1986, it's not 2003, it's today. And the 4 people carrying the answer are doing something right now as we talk that shows you exactly what it means to live inside that question. Today is Flight Day 8, and the crew is doing something that captures the reality of deep space better than anything else on this mission. They're building a radiation shelter, not a permanent one, not a fancy, specially designed compartment. They're taking the supplies already inside Orion, water containers, storage bags, anything with mass and density, and stacking them around the crew's positions to create a makeshift barrier against solar radiation. Picture this: 4 people inside a cabin the size of 2 minivans, piling water bags around themselves like sandbags in a foxhole, trying to block invisible particles moving at nearly the speed of light. Because here's the thing about being outside the magnetosphere, which they've been for most of this mission. There's nothing between them and the sun except whatever shielding the spacecraft provides. And spacecraft shielding is limited because shielding is heavy, and every pound of shielding is a pound you didn't spend on fuel. If the sun erupts, a coronal mass ejection, a solar flare, a flood of charged particles can hit the spacecraft within minutes to hours. And you can't predict it. You can monitor the sun, watch for active regions, estimate probabilities, but you can't know when the next eruption will happen. And if one happens while you're 100,000 miles from Earth, your options are shelter in place with whatever you've got and hope it's enough. That's what they're practicing today. The stacking of bags, the geometry of protection. How fast can you build the shelter? How much coverage do you actually get? Where are the gaps? These aren't hypothetical questions. These are questions that must have answers before we send people further. After the radiation shelter exercise, the crew is going to take manual control of Orion. They're going to steer it themselves, centering targets in the windows, rotating through different attitudes, testing different ways of controlling the spacecraft's rotation and movement. This is the crew proving they can FOY this thing, not just ride in it, fly it. Because on future missions, when astronauts actually land on the moon, when they dock with other spacecraft in deep space, they need to be able to take over if the computers fail. That's what Neil Armstrong did when the lunar module computer was steering him toward a boulder field. He grabbed the controls and flew it himself. Manual control isn't a backup, it's a survival skill. And right now, today, 4 people are practicing that skill while falling toward a heat shield test that the models say should work, but the physics hasn't confirmed yet. Now here's why all of this goes beyond the moon. Because everything I've just described, the heat shield, the communication blackout, the radiation shelter, the manual piloting, even the broken toilet, none of it is just about getting to the moon and back. It's about going further. The moon is not the destination. The moon is the exam. It's where you prove, with real human lives at stake, that your technology and your procedures and your institutional culture are good enough for what comes next. And what comes next is Mars. Think about what Mars actually means. It's not just farther away, it's a fundamentally different kind of mission. 7 months of travel each way, no free return trajectory that slings you home if something breaks. Once you're on the way to Mars, you're going to Mars. Picture the crew 100 days into that journey, somewhere in the dark between 2 planets, the Earth, a pale blue dot shrinking behind them, Mars, a pale red dot growing ahead. If an alarm sounds, there's no abort, there's no rescue ship. There's just the ship you're in and the people you're with. And the communication delay isn't 1.3 seconds like the moon. It's up to 24 minutes each way. Imagine a leak in the hull. Imagine an astronaut calling Earth for help and then sitting in silence for nearly half an hour watching the pressure gauge drop, waiting for a voice that can't come fast enough. On Mars, the crew has to be essentially autonomous, capable of diagnosing, deciding, and acting without real-time help from anyone. Everything Artemis II is testing life support that can sustain humans for days without maintenance, radiation protection that actually works, heat shield performance at planetary reentry speeds, manual navigation, crew health in deep space, all of it feeds into Mars. Every lesson learned on this 10-day mission is a lesson you don't have to learn the hard way on a 2-year mission where a mistake doesn't mean a bad day, it means a grave. And that's why the honesty question matters so much. If the institution can't be straight with itself about a heat shield on a 10-day flyby, how is it going to handle the 1,000 unknowns of a Mars mission? If schedule pressure can bend the safety culture now, when home is 3 days away, what happens when home is 7 months away and the budget is $100 billion? I wrote something once in my appendix to the Challenger investigation report. 1 sentence. And I meant every word of it more than I've meant almost anything in my life. For a successful technology, reality must take precedence over public relations, for nature cannot be fooled. Nature cannot be fooled. You can fool Congress. You can fool the press. You can fool the public, you can fool yourself, but you cannot fool a heat shield. You cannot fool the vacuum or the radiation or the temperature gradient or the speed of reentry. The universe does not read your press releases. It doesn't care about your schedule. It doesn't care about your budget. It applies its laws with absolute, impartial, merciless consistency. And if your engineering isn't up to the standard reality demands, reality will show you in the most unforgiving way possible exactly where you fell short. That's the exam. These 4 people are taking home with them, not can we get to the moon, we know we can get to the moon. The exam is, do we know what we think we know? Have we tested what we claim to have tested? Are our models right, or are they comfortable stories we tell ourselves to stay on schedule? Can we prove it works, or are we just hoping? Now let me tell you what gives me hope, because I don't want to leave you with only the worry. The worry is important. It's the thing that keeps you honest, but it's not the whole story. Here's what gives me hope. Artemis II exists. You're thinking, that's your hopeful point. The mission itself. Yes, and I'll tell you why. After Artemis, I came back with that damaged heat shield. NASA had a choice. It could have rushed to a landing mission. It could have said, the shield is fine, let's go plant the flag, let's make the front page. The political pressure was there. The public appetite was there. 50 years since Apollo, a whole generation waiting. Instead, NASA said, not yet. We're going to fly the same trajectory again, but this time with people, and this time we're going to check everything. We're going to test the life support with real lungs breathing real air. We're going to test the radiation shelter with real hands stacking real bags. We're going to test manual piloting with real pilots gripping real controls. And on Friday, we're going to test the heat shield for real with 4 lives behind it. And whatever happens, whatever the data shows when they pull that capsule out of the Pacific, that will be the truth, not a model, not a simulation, not an engineer's best guess confirmed by a committee vote. The actual physical, undeniable truth about whether this heat shield works or doesn't. That is what a test flight is. It's not a parade. It's not a celebration. It's a question asked honestly, with the understanding that the answer might be uncomfortable. And the fact that NASA chose to ask the question instead of skipping ahead to the answer it wanted, that tells me something. It tells me that somewhere inside that institution, despite the budget pressure and the politics and the $100 billion sunk cost, the part of the culture that I spent the last years of my life trying to protect is still alive. Not perfectly alive, not as healthy as it should be. The heat shield debate proves that. Camarda's warnings prove that. The history proves that. But alive enough to say, before we land, we test. Before we trust, we verify. Before we bet lives on the surface of the moon, we bet them on a flyby where the margins are wider and the lessons are cheaper. Artemis II is not about going to the moon. It's about proving we can come back. That's my question. It's always been my question. Not isn't this wonderful, not isn't this historic, but do you know? Can you show me, can you prove it to me the way nature requires you to prove it? Not with words, not with confidence, not with authority, but with data. 2 days from now, we get the data. Friday evening, Pacific Ocean, off the coast of San Diego. The parachutes either open or they don't. The heat shield either holds or it doesn't. The capsule either floats or it doesn't. And then the engineers crack it open and look at what's underneath. That inspection, that moment, when they peel back the layers and see what the heat shield actually did, not what the models said it would do, that moment is worth more than 100 press conferences, more than 1,000 simulations, more than every confident PowerPoint briefing ever assembled in a government conference room. Because you can fool a room full of managers, but you cannot fool nature. And on Friday, nature gives its answer.